Okay, hi guys. So we'll be continuing on seeing more on the internal energy for an ideal gas. So let's continue on that. So for n moles of an ideal gas, we can write that du would be equals to n cvm dt. cvm dt. Okay. So please remember that this form is only and only applicable for ideal gas. Okay. And let's say now if cvm of an ideal gas is temperature independent, then we can write that delta U would be equals to n cvm delta T. But if in another case, that if cvm of an ideal gas is temperature dependent, if cvm of an ideal gas is temperature dependent, and let's say cvm is equals to a plus bt plus ct square, then by integrating du we have to write, in place of cvm we have to write a plus bt plus ct square dt. This is not small t, this is capital T, integral. Okay, so from t1 to t2, so again we have to integrate it. So delta u comes out to be a t2 minus t1 plus b by 2 t2 square minus t1 square plus c by 3 t2 cube minus t1 cube. Okay, and let's see a note here that for solids, liquids and real gases, solid, liquid and real gases, du by dv is not equals to 0, which was the case in ideal gas. Okay, so for an ideal gas, now let's see the same. Rather for real gas, for ideal gases we have already seen. For real gases, as du by dv at constant temperature would not be equals to 0, so du would still be equals to del u upon del v at constant temperature times dv plus del u upon del t at constant volume times dt dt. Okay, so for a real gas, for rather n moles of real gas at constant volume, we can say that as the volume is constant, then this term would be 0. However, we are seen that this term is not equal to 0 for real gases, so this may not be equal to 0, but as we are talking about a case when we are dealing with constant volume conditions, then this whole term would be 0 because of dv equals to 0. Okay, for real gas, for ideal gases, we have already seen that this term was equals to 0, as for the ideal gases internal energy is just a function of temperature, not of volume. Okay, So this term was 0 for ideal gases. So even if dV term was not 0 for ideal gases, this term was 0, hence making the whole term 0 in case of ideal gases. But in real gases, we have to take a special condition that we are seeing real gas at constant volume. Hence, for making this term 0, whole term 0, we have to make dV equals to 0. Hence, at constant volume, we can say that du would be equals to del u upon del t at constant volume times dt. Now del u upon del t can be written in the form of heat exchange at constant volume, and the same things will follow up. Okay, so again we can write du would be equals to n cvm dt. Okay, because del u upon del t at constant volume can be written as n cvm. This is nothing but, we have seen that at constant volume du becomes qv and qv becomes n cvm dt. So du upon dt at constant volume would become n cvm. Okay, now for real gases, let's take on some cases. First case being, if attractive forces dominates in real gases, then we can write that in gas expansion, dV is positive. Okay, so in gas expansion, distance between molecules increases, or distance between gas molecules rather increases. Okay, and now, so originally we have seen that attractive forces dominate in this real gas. So what will happen if we do some gas expansion? The attractive forces would decrease and potential energy of the gas molecules would increase. And as the potential energy of the gas molecule increase, du would be positive, because internal energy is the sum of kinetic energy and potential energy. So as the potential energy is increasing, change in internal energy would be positive. So we can say that du, rather del u upon del v at constant temperature would be positive. Similarly, if we see the case, rather the point of gas compression, so in gas compression, what we will see, that dV would be negative as the gas is getting compressed, and as it is getting compressed, attractive forces would increase more, because gas molecules are again coming closer and nearer to each other. As a result, potential energy of the gas molecules will decrease, so du would also be negative. And what about this term? Del u upon del v at constant temperature would be again positive, because this term is getting negative and this term is getting negative. So as a result, the ratio would be positive. Okay, now let's see case 2, in which we have been given a real gas in which repulsive forces dominate. Okay, so again we'll be seeing two points inside the case 2, which is if in case of gas expansion, we would have repulsive forces decreasing, and if repulsive forces is decreasing, what can we say about the potential energy? So let's first look at this. So for example, gas molecules are, for example, currently nearer to each other, and they have a lot more repulsive forces in between them. So as a result, potential energy would be higher. Okay, and now they have been spread out so as to reduce the effect of repulsive forces. Hence the repulsive forces would decrease, and here from state A to state B, potential energy would decrease because they are now in more stable states. So potential energy would decrease. So as a result, as potential energy is decreasing, d would have a negative effect on it, and we are talking about gas expansion, so in gas expansion d would be positive, so this ratio would be negative. Okay, now in case of gas compression, when repulsive forces dominates, what we will see? So we will be seeing that repulsive forces would be increasing and potential energy would be also increasing. Why is this the case? Because again, let's suppose this was state A, okay, in which let me make it spread out, because original state is having something like this gas molecules. This is state A, and now it is getting compressed into smaller volume. As a result, the gas molecules will come more nearer to each other, and we have already said that repulsive forces dominate. So here potential energy would be lower. Why? Because it is given that the repulsive forces dominate and they are far away from each other, so hence the system or the state is more stable, hence potential energy would be lower. And in this case, when it is compressed and made to stay, the gas molecules are made to stay nearer to each other, when already the condition there is that repulsive forces dominate, hence we are making the state B as more or rather less stable, hence potential energy would increase. So, and obviously repulsive forces would also increase because the gas molecules are brought nearer to each other, hence repulsive forces increase, potential energy increase, d would also have a positive effect, and we are seeing gas compression, so dV would be negative, hence du upon dV at constant temperature would be negative again. So with this we come to the end of this lecture. So till then, good luck and goodbye.